Okay, hi, my name is Arnar Vilhjálmsson and I'm going to give you a status report on this project resistivity survey of Grímsvötn. It's a collaborative work of 5 partners, Iceland Geosurvey, the University, GEORG, of course, University of British Columbia, and GEONIX Limited. And here you see the overview of the lecture. We will look at the initial objectives of the project, look at the problematic data acquisition, and the next steps in this project. Now, because of unforeseen events and quite a lot of problems during the data acquisition, we redefined the project, and we will also go through the redefinition of the project. But let's begin to have a look at Grimsvötn. We don't have a pointer, no. Okay, you can see the red dot on the glacier, Vatnajökull, where we have this big caldera, Mickey Mouse-like caldera. And this is one of the most powerful high-temperature geothermal fields in Iceland, and in the world, actually. It's the most active volcano in the world, in Iceland, in terms of eruption frequency, with over 60 eruptions the last 800 years. And it's overlain by ice, and the ice works as a natural calorimeter. And the estimated thermal output is around 2,000 to 4,000 megawatts. And we can see the eruption sites in the southern rim of the caldera, and the eruption in 2011 was approximately at the same site at the one in 2004 in the southwest corner of the caldera. Now, the initial objectives of the project was to map the spatial extent and depth of resistivity anomalies within the Grimsvötn caldera, map the location and extent of magma bodies in the uppermost 3 to 5 kilometers, and assess the thermal release from pristine geothermal system for comparison with other geothermal system under full exploitation. Finally, the plan was to build conceptual model of the system using the resistivity data along with gravity and magnetic data measured by Milsom and Magnus Tumi Guðmundsson, and also compare these data set to seismic data. However, everything did not go as planned. The first field mission was planned in spring 2010 or early summer, but in April same year, the second phase of Eyjafjallajökull eruption spread ash all across Iceland and also across Europe, and this ash distributed unevenly on the surface of the glacier, and this irregular spreading caused irregular melting of the snow, and the surface was like this. And a trip that was supposed to take 2 hours took 14 hours from the glacier boundary to Grímsvötn, and the fuel consumption was gigantic. We spent more than 1,000 liters in 1 week. That was supposed to last for 3 weeks. So travel costs were very high, and the efficiency reduced considerably. And we had planned to locate 2 or 3 current loops and make soundings at 80 to 120 sites, but we only managed to place 1 current loop and 30 soundings. There was one more problem. There was some limitation with the MT equipment that we had planned to use. Iceland Geosurvey owned this MT equipment, so we had to rent another equipment at great cost. And part of that equipment failed, so we only had 50% of source power, so the data quality was reduced. But we plan to do better in the spring 2011, early summer. We knew what to expect on the glacier. We had developed some work procedures to maximize the efficiency. But then this happened, another eruption, and now it was in Grímsvötn itself. And it was, of course, not possible to make the measurements during the eruption. And there was also a problem with, we couldn't, if we would collect new data, they would be incompatible with the old one, because the plan was to make a 3D inversion of all the soundings acquired in both 2000 and 2011. So the project went on hiatus and was just recently redefined and revived, really. So I'm just going to look at the data acquisition. We surely managed to do something, and this method has never been used before in Iceland. It's some sort of a temp sounding, off-central temp sounding, and we go very far off-central, so it's far off-central temp sounding. It's some sort of variation of a low temp, which is a long offset TEM sounding. In a normal TEM here in Iceland, we are using loops of the size 200 to 300 meters, 300 by 300 meters, but this one is 2 by 2 kilometers and is huge. And we use 3 equipment to collect the data. Two of them collected 3-dimensional data, but one only 1-dimensional. Now what is done here is there is a current put on this loop, the square loop, the TX square loop, and that induces currents in the ground, and those currents induce, well, the magnetic field that is induced in this loop induces currents in the ground, and the secondary magnetic field is then measured. And the plan was to locate a source loop at several locations and then make measurements at the same sites in each loop to resolve the 3D the 3-dimensionality of the resistivity in the Grimsvötn. So here we can see the loop. The blue square is the loop we managed to make, and the red diamonds are the soundings that we made. There were 30 in all. Most of them was inside the caldera, but the 6 in the south were on a mountain, up on Mount Grímsvötn. So here we have example of inversion of the data. It's a 1-dimensional inversion of 3-dimensional data, actually. And we can see like the sounding 893, it is located inside the caldera itself. Maybe I can just show you. It's the sounding here. And we can see that there is a very good correlation between the ice thickness, the blue line there, and the thickness of the ice according to the model. And just to explain, the dots here, this is the data, and the line through the dots is the forward calculation of the model. So we are fitting the data very well. And the other point, 871, he was on top of Grímsvötn. There you can see we have very thin ice. It's less than 70 meters, but still, according to the model, the ice is around 400 meters. That's because of 3D effects. We are measuring far outside the loop, and the current in the ground are under a very big area where the thickness of the ice is much higher than under each side. So this is an example of the 3D effects. So here we have a resistivity horizontal cross-section at 1,000 meters above sea level. That's about 400 to 600 meters depth. And we can see well, beautifully shaped anomaly, but unfortunately it also correlates very much to the loop. So we cannot read too much from this image. We have this high resistivity in the center of the loop, surrounded by low resistivity, but not particularly low. And this is actually immediately below the ice. If we go at greater depths, we can still see this form. We have low resistivity surrounding the loop with higher resistivity in the center. And I must remind you, this is still just 1D inversion of a 3D data, and we really need to model the glacier and the bedrock beneath it and make some forward calculation to see if we can really trust these anomalies or if they are just artifacts from the geometry. At greater depths, here we are 300 meters above sea level, 1100 to 1300 meters below surface. Here we have just low resistivity under most of the soundings. And it might be due to some low resistivity body in the center of the area, but due to the 1D inversion, the low resistivity is smeared out over the whole picture. Now here is a cross-section lying east-west through the center of the loop. This is in some way a conventional geothermal system or resistivity image of conventional geothermal system. We have a low resistive layer underlain by higher resistivity, but in a typical system we would see the layer like bulging up in the center, but not being so thick in the center, with higher resistivity underlying the low resistive layer. Here we can also see the white line atop that shows the thickness of the ice, and there is a very good correlation between the ice thickness and calculated resistivity in the soundings. And here we have a cross section lying north-south, and we can see there are very extremely low resistivity at either end of the profile, and that is probably due to some sort of 3D effects, and it's really necessary to test this model for 3D effects. Here we have this look more like conventional high temperature geothermal field. This layer is bulging up in the middle and is underlain by higher resistivity. So the results is that we still have to work with this data to get some trustworthy results, but we still know that this method, this far-off central method, it works, but it would just be better to have more source loops and three-dimensional code to process the data. If we go again to measure at some times, we have fieldwork procedures that have been developed and would ease things if we go again. And we have also adapted 1D immersion codes to this type of data, or it was actually the work of Knútur Árnason, who is sitting in here, to do that part. So we have the 1D immersion codes to work with this data if we can collect more. We still have to work a little bit more with this data. We have to check if these artifacts that is seen around the loop is real or not. And we can do that by model the glacier versus the bedrock. And we can also transform this 1D dimensional resistivity model into a 3-dimensional grid and forward calculate it and see how it fits to the collected data. And in a more distant future, and a 3D inversion might be done to the data, but that would require us either to write a new inversion code or get access to a code abroad, and that will not be part of this project. Now, due to this problems, this extra cost during the field work and the change of resistivity settings in Grímsvötn, this project was redefined. It has been split up in 3 tasks. The first thing is to interpret this data we already have and to compare it to other geoscientific information, such as seismic data and gravity and magnetic data. The second phase is to measure a few MT and TEM soundings in the uptipping area, and I will explain that further later. And then to see to address the question of the nature of a deep conductor that is found under most of Iceland, and I will briefly introduce it in the next slide. In the 1970s and 80s, a limited countrywide MT surveys were conducted in Iceland, and they observed a low resistivity at 10 to 25 kilometers depth under most of Iceland. The resistivity in this layer is 5 to 30 ohmmeters. It's shallowest under the volcanic zone and deepening away from it, but it's not observed under the south coast. The nature of this layer has been questioned, or people that don't know what exactly is causing this low resistivity, and that is part of this project to find out. Now, well, this layer seems also to be related to geothermal areas, as it domes up under most of Icelandic high temperature geothermal system, and we have seen evidence from numerous places like Krafla, Námafjall, Þeistareykir, and Vonarskarð. And this low resistivity conductor has also been observed in new empty profiles outside the volcanic zone, like in Eyjafjörður and near Upptippingar. Upptippingar is a key area in the research of this deep conductor, event characterized by a deep-seated earthquakes happened there in 2000 and 2008, and what is remarkable about these earthquakes that they occurred under this deep conductor, and we rarely have any earthquakes below this conductor. So the information we can read from the seismic data from this area and along with resistivity data can give a very important information about this layer. Now, Upptippingar is also very close to Askja, so we can measure a profile from Upptippingar towards Askja and see how this conductor behaves away from the volcanic zone to a high temperature geothermal field. And in 2007 and 8, 15 NT and TM pairs were measured in this area. Here we can see Herðubreiðar Tögl in the upper left corner, and Upptippingar are in the center of the figure. The yellow stars are earthquakes that occurred in 2007, and the red ones, and also the red ones actually. But the earthquakes, the green stars with white fillings were earthquakes in 2008. And if we have a look at the resistivity cross-section, the lower one, UC1, immediately north of Upptippingar, and then we project the epicenters of the earthquakes onto the cross-section, we can see this image. There we can clearly see a conductor at maybe 1 kilometers depth, and then there is this deep conductor at 10 to 15 kilometers depth. And the earthquakes, they started below this layer, and they stayed there for a few weeks before they started to migrate upwards. And as you can see, it didn't go straight up, but went to like diagonally up through this layer. And we can also see that earthquakes, the red earthquake that was near Herðubreiðartögl, that they have been relocated by Susalu and Bob White, and none of them is inside either of the layers. So this gives some hints about how brittle or ductile the crust is inside this layer. So a field mission was planned the summer 2014, and now this happened. But fortunately, we were there in July, so it didn't affect our work. Actually, the field work went very well. We made 30 new MT and TEM pairs. We made 2 profiles through the earthquake swarm. If you see the blue dots south of Upptepingar and then up on the east side, that were new measurements made through the earthquake swarms or above the epicenters of the earthquakes. And then we measured a profile towards Askja to see how the conductor behaved when we get close to a high temperature geothermal system. And that's the blue dots on the left side of the image. And this was only collected last summer. The data has not been processed yet. But 3D resistivity images will be made for this year and published. And the resistivity will be compared to seismic data. So last but not least, the nature of the deep conductor. This layer has for a long time been a source of the constant debate of interpretation of the temperature distribution and rheological and physical properties of the lower crust and upper mantle beneath Iceland. And this is the first time that a study is focusing on this layer in particular. Geoscientific data from across Iceland will be used from Upptipingar and Krafla, Hengil, Eyjafjörður and Reykjanes, along with seismic data. We might possibly be able to identify isothermal planes to calculate the natural thermal output of geothermal systems, but that was actually one of the aims of the initial project of the Grimsvötn project. Now this project is financed partly by IMAGE, which is a European Union funded project and has synergy with the project Deep Roots of Geothermal System of GEORG. So if I just summarize briefly, much less data were collected in Grímsvötn than we had planned. It had several problems due to eruptions in Eyjafjallajökull and in Grímsvötn. We have done 1D interpretation, but we still need to finalize the interpretation with another data, like seismic and gravity. Collecting of data in Upptipingar has been completed, and using the dataset from 2000 and 2008 and interpreted with seismic data will be published this year. And then in early next year, the nature of the deep conductor, and actually work will also start in this year on the nature of on the deep conductor. So yeah, thank you.